talking about map inference. And this is a fun topic because it sort of pushes in a different direction, just algorithmically than sort of how we have been thinking so far, where up until now, we had been kind of concerned with finding these continuous marginal variables, continuous marginals of variables. And for map inference, we're now really trying to find the most probable assignment to the variables, and this is really a combinatorial optimization problem. And so the solutions that we resort to here draw on algorithms that sort of come out of this rich field of combinatorial optimization in mathematical programming. Okay, so homework 2 is due on Saturday, October 12th. And then, is this already out of date? No, October 7th is today, so this is the last chance to switch. Though it might be too late because you need so many signatures on a late add form, so just be careful if you're thinking of that. And then I had canceled my office hours after class today. They're now back on, they're uncanceled. So feel free to ask me questions after class. So we were using, in some sense, as motivation for this section, this notion of minimum Bayes risk decoding. And so I want to bring this back up again. We said that a minimum Bayes risk decoder is one that returns a variable assignment with minimum expected loss under the model's distribution. Okay, so here you remember this notion of an expectation under the model's distribution. We talked about it last time in the context of computing the gradient of a conditional random field for a log linear parameterization of it. And so here we're seeing that same sort of expectation under the model's distribution over the output variables y given the input x. And the difference is that now we're taking an expectation of an actual loss function. Okay? So this to me is one of the most interesting equations that shows up in machine learning. Because what we're saying here is that neither y hat nor y is bound by the left-hand side of the equation. Right? So the left-hand side of the equation is just the decision function that you want, right? It's some h of x that should return a y, a prediction y, namely a y hat. And so what we're saying is that the y hat that you should return should be the one that minimizes this expectation. Well, if you knew what the true y was, then you would just return the argmin of L of y hat and the true y. But you don't know what the true y is, right? This is at test time where we're trying to make a prediction. And so what we need to do is return the y hat that minimizes instead a quantity that uses the current model parameters as your best estimate of what the true y is. Okay, so essentially what you're doing here is you're saying, you know, if we were sure what y was, we would just drop this whole expectation. Because we're not, we're going to sum over all possible true y's. And for each one of them, we're going to say, well, my model thinks that this particular true y is 0.7 probability likely. That's a lot of weight. And so we're going to take the loss of y hat with respect to that y very seriously. Whereas there's going to be some other y that has really low probability, say 0.00001. Okay. Well, the model is pretty confident that that's not the true y. And so we're going to say the loss between whatever you're predicting and that y is less important. It gets downweighted. So a minimum Bayes risk decoder is just a decision function, h theta of x, that you get when you instantiate this equation for a particular loss function. And so what's interesting about this is that the loss function itself, depending on how you define it, it may or may not be easy to come up with an algorithm that efficiently returns h theta of x. So why is that? Well, think about what you're writing down here. This is an argmin over y hats, looking at all possible y hats, and this is a summation over all possible y. Yeesh. I mean, computing marginals requires just the summation over y's, and doing map inference just requires min or max over a set of y's. And now we're putting the two together into one and saying we're going to do both. Okay? So this feels like the sort of thing that, if we're not careful, might have some double intractability to it. But it really depends on the actual loss y. Okay, so if the loss decomposes perfectly over the variables, then the minimum Bayes risk decoder also decomposes over the variables. Namely, if you use something like Hamming loss, then the actual loss simplifies to just being an argmax over individual y hat variables. The one that we're going to be interested in today is the 0,1 loss function. So this loss function says you're going to have loss equal to 1 minus an indicator function of whether the two are equal. Okay? So substituting that back into our equation for a minimum Bayes risk decoder, we see that we still have our argmin and our sum, but there's going to be many terms in this summation where 1 minus that indicator function is 0. Only one of the terms in that summation will have 1 minus the indicator function. Other way around. So, should be careful. So there's exactly one of these for which the indicator function will be 1. And, so this is an indicator that they're equal. Maybe I would usually write it like this. So, for the term where y is equal to y hat, this term is 0, and then all the other ones are value 1. So what that means is, if we're trying to minimize this sum, then what we're really doing is, so now we can actually expand this out. So imagine taking this probability and multiplying it by 1 and by negative of the indicator. So just distribute that probability between those two. And so what you'll get is one term that's just summation over the probability of y, and then minus another term which is summation over all y's probability of y given x times this indicator. Okay. So this term is just constant with respect to y hat. So we can just discard it entirely. And this term, negative sum over p of y given x times the indicator, is only non-zero for the value y hat. Which means this whole thing is going to be just equal to p of y hat given x. Okay, this is, should I just write this out? I should write this out. This is such a mess. Let's just write this out. And this is such a lovely little decomposition. It just takes us 2 seconds. So what we have here is h theta of x is equal to arg min over y hat of a summation over all y of p of y given x, that's according to our model, times our loss function, which is 1 minus this indicator function of y hat equaling y. So all I did here was I said, well, let's take everything in brackets here and divide it into 2 summations. So we'll say we still have our arg min over y hat, but now we're going to have a sum over y of p of y given x, that's one of them, minus a sum over y of p of y given x times that indicator function, y hat equals y. And the observation here is this is constant with respect to y hat. And this is equal to the probability of y hat given x, because all of the other terms in that summation are 0. And so what we get back then is that this is simply arg min over y hat, p of y hat given x. Oh, thank you. We have to, so it would be arg min of, let's do this carefully here. So it's of the negative probability, and then we flip it to an arg max and drop the negative. And there is our minimum Bayes risk decoder for the 0-1 loss function. Okay, so this is the case for a 0-1 loss function. We can also find that if you know, so if L of y hat of y decomposes in the same way as p of y given x, there's this question, which is, can we efficiently compute h theta of x equal to the MBR decoder? So the answer here is yes. And I think we'll have to say that this is such a lovely little problem to work through that we'll leave it for you to do on your homework. You guys want to just make a note of that? This sort of decomposition kind of follows naturally with the way that p of y given x is specified. And if p of y given x decomposes according to some factor graph, and the loss function also decomposes according to the same factor graph, then you can get back something efficient. So long as you have an efficient way of working with p of y given x. Yeah.
What do you mean decomposes, I guess? So like, yeah.
So just that, so if p, so we spent all this time talking about factorizing p of y given x according to a factor graph, where it's a product of a bunch of terms, one for each factor. So in the same way, if you can write L of y hat y such that it factorizes into a bunch of terms, one for each factor, then we would say that they decompose in the same way. So we'll make that precise in the homework. So this is the kind of key problem that we want to actually, oh yeah, another one.
I'm still confused as to why all of the other p of y given x's go away, so you're left with negative p of y hat given x.
Oh, sure. So the question is, for what values of y is the indicator function y hat equals y equal to 1?
Oh, so that would be when y hat equals y, so then
So there's only one term in that entire summation that is,
zero.
yeah.
And then the other ones are constant, so that's why you can minimize and maximize into that one.
Exactly, exactly. So Okay, so where are cases where you might actually have a loss function that that is like this 0-1 loss? Like where are cases where you might not want something like Hamming loss? You might want something that gives you back a single assignment to the variables that has highest probability. Can you think of any cases like this?
In N-way classification, where we want to calculate distribution of N classes.
So if you're doing N-way classification, do you mean, but here we're assuming that we have multiple variables. So are you saying you would decompose the N-way classification into, say, N indicator variables? Yeah, so if you have, so maybe let me generalize that a little bit to say, if you have, say, N variables Y, where certain joint assignments to them just don't make any sense, right? Then this might be a case where you really do want a single jointly likely assignment, right? So putting this another way, imagine if you had a coloring problem, right? And you had to color all of these variables such that no two variables no two adjacent variables in the actual factor graph had the same color. So if you had such a coloring problem, then you could imagine that we might want, so if we were to do something like Hamming loss, what could go wrong? Well, if we just did Hamming loss, maybe we're in a setting where the most likely, so let me give a valid coloring here. This will show up in a second. Okay. So this is a valid coloring of this graph because no pair of adjacent variables in this graph are colored the same way. So if we had a situation like this, and you used a Hamming loss function, it's possible that you could get back an assignment to the variables that was something like blue, 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 and blue, right? Maybe each variable, independent of the other variables, is most likely to be blue. But when you consider them all together, what you want is an assignment to all of them that gives you back something cohesive. Okay, so in general, there's lots of problems of this variety. I think a great one is actually if you're trying to populate a Wikipedia info box with information, say about a person. You want to populate the fields in that Wikipedia info box in a way that is sort of logically consistent. So you don't want to describe aspects of the person that would make sense, you know, if they were a world famous soccer player, but they don't make sense if you're separately describing them as an important financial tycoon. And so this notion of sort of having many output variables that interact sometimes means that you do want to return an assignment to variables that is sort of internally consistent. Okay, so how can we do this? Well, we need to take a little bit of a divergence into talking about linear programming and integer linear programming. And then once we have these under our belt, we'll kind of double back and think about how we could use these techniques to actually solve this problem. Okay, so let's start by thinking of a linear program. And a linear program is it's going to be one of the following form, where we say, let's actually we'll start with just a simple example here, and it's going to just be a two-dimensional example. And so we're going to say that our goal is to maximize some linear objective function over variables x. Okay, so the objective function we'll work with here is going to be x1 plus 2x2. And we're going to have some constraints. So we'll write such that, and then our constraints look like x1 is greater than or equal to 1, and x2 is greater than or equal to 3, and x2 minus 3x1 is greater than or equal to -5, and x2 minus 1/2 x1 is less than or equal to 5/2. So what we're looking at are sort of two parts of the actual program. This is a linear program, and it consists of an objective and some constraints. And we can actually depict this objective and constraints in 2D here, where we say, okay, the variables over which we're optimizing are x1 and x2. And the range over values, say 1, 2, and 3 on the x1 axis, and 1, 2, 3, and 4 on the x2 axis. And so now what we need to do is actually draw out all the intersection of all of the feasible half spaces given by these linear constraints. Okay. So each of those linear constraints is defining for us some hyperplane. Okay. So here, let's do the easy ones. So x1 is greater than or equal to 1. Okay. So that's just going to be a half plane. Sorry, a hyperplane that goes like this. And we have x2, oh, and then we're going to be on the right side of that hyperplane, since we're greater than or equal to it. And then we're going to have x2 is, let's see, do I want greater than or equal to 3? I think I probably want less than or equal. Oh, no, that's just a typo here. So we're going to do x2 is also greater than or equal to 1. Okay, so now that looks like another horizontal hyperplane like this, cutting across. Okay, now we have this x2 minus 3x1 greater than or equal to 5. And that one is actually going to be, so it's going to have an intercept of -5, but it's also going to pass through this point 2, 1 with a slope of +3. So it will also pass through this point 3, 4. And then the last constraint is going to be one that has an intercept of 2.5, but I think it'll pass through 1, 3 here, and also 3, 4. So what we're left with, based on these constraints, is a region where if we take the intersection of all of these little linear constraints, we get back this blue region. Okay, why? Because we need to be on the greater than or equal to side of x1 equals 1, and on the greater than or equal side of x2 equals 1, and on the greater than or equal side of this diagonal line, and on the less than or equal to side of the other diagonal one. Okay. So this inner part is what we call the feasible region. And we can also depict the objective function. And we do that by thinking about the objective as the dot product of, say, a vector 1, 2 with a vector x1, x2. And thinking about it this way, we can say, well, that would be like an objective function where the direction of steepest descent is pointing up at this direction following the vector 1, 2. Sorry, except I scaled that wrong. So here the vector 1, 2 is going to point here. And so you can imagine if we were to draw a contour plot for the linear objective function, it's kind of an uninteresting objective function, right? If you're used to solving quadratic objective functions or non-convex objective functions, those usually have some interesting topology. The contour plot for this one is just going to be a bunch of contour lines that are that are orthogonal to this objective function here, where the further you go upward in that direction, the higher the value of the objective function. So we should probably make a few small definitions here. So we say that the problem itself is, so actually let's define the actual feasible region. So the feasible region is a polyhedron and possibly unbounded, meaning that it could actually have sort of an open side to it, right? If the only two constraints we had were x1 greater than or equal to 1 and x2 greater than or equal to 1, then what's the solution to this problem? x1, x2 equals infinity. Right? We're just going to run off in that direction. Okay. So in this case, we have a bounded feasible region, and we would say that the problem is infeasible if the feasible region is empty. So if the feasible region is empty, this just means that there's no solution to this actual problem. Okay. So in the case of the problem that we laid out here, the point that maximizes that objective function subject to these constraints is going to be at the very edge up here at 3, 4. This is the actual optimum. So x1, x2 equals 3, 4. So if you're working with linear programs, though, it's sort of useful to understand how we sort of traditionally write them down. And so the standard way is called a linear program's standard form. And writing a linear program in standard form is just going to amount to writing the problem as a max of C transpose X such that AX is less than or equal to B, and each variable xi is greater than or equal to 0. So what we have here is a max problem or a max objective function. So that's ingredient 1. Ingredient 2 is that our inequalities are in this less than or equal to form. And then lastly, that we have non-negative variables. So just so we're clear here, when we write it out this way, what we're assuming is that C, X, and B are vectors, and then A is a matrix here. And then further, we assume that X are variables, and C, B, and A are constants. So this is how we typically write them down, and the sort of important bit about this is just that we can actually convert any linear program to standard form. So namely, every LP can be written in standard form. So just so you can actually see that, so let's run through a couple examples here. So if your original LP was written with a min instead of a max, well, you could get to a max just by negating the objective. Right? So that means, if you have min C transpose X, that can just become max negative C transpose X. And then this applies similarly if you wanted to go from, say, a greater than or equals constraint to a less than or equals constraint. So you can do this by negating the constraint. So here, if you had, say, A1 x1 plus A2 x2 is greater than or equal to some b, that's exactly equivalent to a constraint that is negative A1 x1 minus A2 x2 is less than or equal to negative b. And okay, so what if you have an equality constraint? Can you convert an equality constraint to standard form? So let me give you an example. So A1 x1 plus A2 x2 equals b. Yeah.
At a constant.
At a constant somewhere.
Like a positive value.
I don't think you can do it with a constant. Any other ideas? Yeah. Oh, A1A200. So where did the zeros go? Oh, but remember that AX needs to be less than or equal to B. Not equal to. I want to get rid of the equality.
You can do less or equal to b plus 1 greater than b.
Yeah, so, or even simpler, we can just do, so just the greater than or equals to and the less than or equals to version of this. So a1x1 plus a2x2 less than or equal to b. And then also add a1x1 plus a2x2 greater than or equal to b. Okay. If both of these are true, then it's got to be equal to. And we already know how to convert a greater than or equal to a less than or equal to. So let's see. So there's more of these. So like, for example, if you have a variable with an upper bound, so this would be like if you have a variable, say, xi that is less than or equal to some u, you can actually do a tricky conversion, which is you add a new variable, and we could say that the new variable is just going to be some wi, which you define to be equal to, say, u minus xi, with wi, and with the usual non-negativity constraint. 0 is less than or equal to wi. So if everywhere that you have xi, you replace it with wi or u minus wi in your actual program, and then you just let wi be a usual non-negative constraint, then you get back a variable, and you get this constraint for free. You don't actually have to add an extra constraint to account for this upper bound. So maybe that's just getting fancy. You can also do things with, if you have like a variable with an interval. So this would be, I'll skip this one. I'll say, we'll leave that as an exercise. And then, oh, the last one is kind of cute. So if you have a free variable, so this would be a variable that's just got no constraints on it, right? Then in that case, you can have a new, or two new variables, x prime and x prime prime, such that x is going to be equal to x prime minus x prime prime. And then we just have that 0 is less than or equal to x prime, and 0 is less than or equal to x double prime. And so just by sort of replacing all of your x's with these two variables in your program, now it's just as if you had a free variable that could be either positive or negative. So, so the point is that you can always take any linear program and convert it back to that form. And the reason that we do that typically is actually so that you can then efficiently carry out sort of the standard algorithms for these things. So the most commonly used algorithm is the Simplex algorithm. And I think actually, just sort of in the interest of time, we're going to just do this in pictures. So the sort of pictures version of this, so we're going to do an example here. And I'm going to attempt this in 3D, probably end badly, see how far we get. So we're going to say we have three variables that we're optimizing over. Okay, and those are x1, x2, and x3. And so remember that any linear program is defining a polyhedron. And so here what we're doing is we might have a polyhedron that looks something like this. And it's in 3 dimensions, so now we're going to kind of imagine this part of the polyhedron kind of coming out away from the slide. So you can kind of imagine some polyhedron in three-dimensional space, and this part is sort of sticking out away from us. And then we have an objective function. Well, that's just a gradient, or sorry, it's just a vector pointing in the direction of increase. So maybe it's pointing in this direction. And the key idea behind the simplex algorithm is that the optimum is always at a corner of the polyhedron. And so, the simplex algorithm just walks around the corners greedily. So you could think of this as sort of consisting of an iterative process where you pick some initial corner. And while that sounds like an easy prospect, even just picking an initial corner is actually a little bit tricky, right? Imagine just with our tiny two-dimensional example up here, if I said, okay, here's some constraints, now give me back a point inside that region. Without drawing the picture, writing an algorithm to give you back any point in that region might actually be a little bit tricky. Okay, so just to say that step one here is non-trivial. But once you've picked an initial corner, then the next step is to inspect all the adjacent corners. So you could imagine if maybe the initial corner that we pick is this one, the bottom corner, then we're going to actually inspect the three adjacent corners to that one. And of those adjacent corners, pick the best adjacent corner. Where here, best just means one with the highest objective. And if there's no improvement, then you stop. So you could imagine then that the way that this might proceed is you start off at this red point in the bottom corner, and then you inspect the adjacent corners and you pick this one. So once you've picked that one, then again you're going to have to inspect the corner that you had already looked at, plus a bunch of new ones. This one, and this one. Looking at all of those, maybe in this case, the best one is this outer corner here. So you move to it, and then again you inspect the adjacent corners. You certainly don't go backwards. Maybe you move forwards to this one, and then finally land at the optimum corner up there.
Does the algorithm assume that the optimum is always in the corner, or is that a true statement?
Oh yes, sorry, this is a true statement. So it's always the case that the optimum is at a corner. Again, let's just do this in pictures. So in pictures, the reason that the optimum is always at a corner, you can actually sort of see based on the actual contour plots of the objective function that you're optimizing versus the constraints. Okay? And so what happens is, So if we were to, the way to actually sort of explain this formally is to talk through the method of Lagrange multipliers. And if we did that, we would be able to make a really precise statement, which is that the gradient of the objective function is actually going to be tangent to the gradient of the constraint function.
All of them combined.
If we combine them all into one. So think of one function that describes that that feasible region. And so the point at which we get this tangency is always going to be at some point where, so the constraint region we could think of as, let's actually draw a new picture here. So we'll just say this is a bit of an aside. Method of Lagrange multipliers. Let's say this is not sort of proper material for the course at the moment. We'll actually probably come back to this topic, but I just don't want to sidetrack us too long. So if you think of the feasible region as consisting of a bunch of contour lines, and the real feasible region is just one of these contour lines, and then your objective function is a bunch of contour lines as well. There's going to be some point where the contour lines of the objective function are tangent to the contour line of the feasible region, and that's always going to happen at a corner. So you could kind of think of it like, for any line, if you just start sliding it towards a polyhedron, it's going to hit a corner. Except in one specific case. And what is that case? When would you not have, if you were imagining sliding, so you have the contour lines of the objective function. Okay, over there is the highest possible value of the contour line. And this is slightly less, slightly less, slightly less, slightly less. Oh! If it lines up exactly with one of the edges of the feasible region, then that whole edge is going to be, any point on the edge is going to be maximum. But that means that so long as you land on one of these two corners, you've found a maximum. So it still works.
What if your constraint region is unbounded? Then, like, how is it going to work? Because you don't have corners. You do not want it.
Yeah. So this is where things get interesting, and so you actually have to be able to detect when there does not exist a corner, right? So if your feasible region is truly open, right, and this just goes on forever, you need to be able to detect that at this corner, one of the sides is completely open.
In that case, would your optimum just be infinity or something?
Yeah,
Because,
exactly. So this can happen. And so often it's useful to know that this can happen, because if you're defining a linear program that you're pretty sure should have a valid solution, and what you get back is that the problem is unbounded, then maybe you've actually sort of specified your problem incorrectly. Okay. Okay, so we'll at some point come back to sort of this discussion of method of Lagrange multipliers. So the other algorithm that I just want to highlight here is that of the interior points methods. Now there's many different interior points algorithms, and the name essentially gives away exactly what it is that these algorithms are doing. So if you have some feasible region and some direction of greatest increase for the objective function, then you start at some initial point inside the region and you move around inside that region until you hit the optimum. So here, the key idea is always move within the feasible region. Okay, so this is a whole family of algorithms, and sort of the key aspect of interior points methods is that they are polytime algorithms, and meaning that they can for any given input they will complete in time polynomial in the size of the input. And the key thing to note about the simplex algorithm is just that this is not a polytime algorithm, but it's common in practice. So essentially, it's so efficient to actually implement the simplex algorithm that people tend to use it more frequently than interior points methods. Essentially, like getting an interior points method that on paper is polynomial time and is practically fast when you implement it is actually a little bit tricky. So, yeah.
Why doesn't the simplex algorithm find local maximum? Like, why does it always find a local maximum?
Oh, why doesn't it get stuck?
Yeah.
I mean, I guess like a proper answer to that question would be for us to prove that the feasible region of a linear program is convex, and that that going in any direction in a convex region has a unique, or well, it's not actually strongly convex, so it's convex. So there's not a unique maximum, but so like basically the key property that we would just need to show is that the feasible region of any linear program is convex. So if you can prove that, then you're basically done.
Isn't the objective function like a plane? So it would be like both convex and concave, right? Like.
So, but the more important detail is that the actual feasible region is convex. So the objective function is just a linear function. So in that sense, yeah, it's convex, and also concave. The question is our constraint set giving us back a region that is also convex? That's the more important question, and the less obvious one to prove. Okay. So now, what I want to do is move to a discussion of problems that are non-convex. Okay. And we're going to get there with just a tiny tweak to our definition of the linear program, and it'll give us what we call an integer linear program. Or ILP. So an integer linear program is going to be one that, sorry, this isn't just an example, this is sort of an ILP in standard form. And so an ILP in standard form is going to look just like a linear program where we have max over the variables x of a linear function of x, so C transpose x, such that AX is less than or equal to B, and also 0 is greater than or equal, or rather 0 is less than or equal to xi for all I. And then we have this additional constraint that each variable xi is in the set of integers. So what we have here are really two programs. So the important one is the entire thing is what we call the integer linear program. But if you were to take everything except for this last constraint, then what you're left with is called the LP relaxation of the ILP, which just equals everything except the integer constraint, or constraints rather. So problems of this form are particularly interesting. And if we just draw a simple picture of one, you can immediately see why they are likely to cause us some trouble. Thanks. Okay, so here, let's suppose again we have variables x1 and x2, and I'm just going to depict the possible integer values of x1, x2. So this is just a grid of all possible integers that you could get for x1, x2. And you could imagine this grid kind of expands off in either direction. So imagine if the feasible region defined by the LP relaxation looked like this. So suppose we had something that cut through like that, down here, like that. So this blue region is the LP relaxation. This is what we would get if we didn't have the integer constraint. And the set of feasible points for x1, x2 in the ILP are all of the black points inside the blue box. So the ILP feasible points are all black points in the blue box. So crucially, what we have here is that if our objective was a vector, say, pointing in this direction, okay, then what is the optimum of the LP relaxation?
Corner on the left.
Yeah, that top corner right up here. So this is the opt of the LP. What is the optimum of the full integer linear program? Should label these as so 1, 2, 3, and 1, 2, 3, 4. So what's the optimum of the ILP? I think it's probably 2, 1. So this is an integer point, and it's inside the feasible region. So, or sorry, what did I say? 2, 1, 2, 3. Yeah, so the point 2, 3 is inside the feasible region, and it's as far in the direction of the objective function as we could go. I think maybe it's a toss-up between 2, 3 and 1, 2. So the key idea here is that just by imposing this integer constraint, suddenly the whole shape of the problem looks rather different. Okay, so let's define one more type of problem here, which is a mixed integer linear program. And a mixed integer linear program is going to be one so the mixed integer linear program is going to be just like the integer linear program, except that now we're only going to have the integer constraint on a subset of the variables. So we'll say that we have the same constraints as before, but that only some of the actual xi's in some set S, where x is a subset of, say, the integers 1 to n, if we have n variables here. So only some vars are integer. So inspecting our picture above here, how would the problem change if suddenly I said, okay, only x2 needs to be integer? What is the set of feasible points for the mixed integer linear program that results? So we have our same square for the LP. What was the set of? Yeah, it would just be horizontal lines cutting through this box for each integer value of x2. So this would be if x2 was in z, but x1 was not in z. Or rather, that's the wrong thing to say, but x1 was in the real set. So, okay, so now we have this picture of all of these sort of different ways of specifying problems. And we need to kind of be specific about how we could actually solve a mixed integer linear program. So I want to give some quick background on non-convex global optimization. So imagine that our goal is to optimize over this blue surface. So this is not necessarily a linear problem anymore. It's just some complex non-convex problem. And we have different projections of that objective function onto the different planes representing the different axes. And you could imagine one way to solve it is by standard local methods. So you start at some initial point and you maximize locally by just climbing up to the top of the nearest hill. This is a good idea, but you might not get the best of the hills, right? So we say that a relaxation of your objective function provides some upper bound on that surface. So here we're looking at a linear relaxation of that non-convex objective function. And we say that branching is basically partitioning the search space into subspaces that will enable tighter relaxations. Okay, so here's what I mean. If we branched on the value of x1 being either less than or equal to 0 or greater than or equal to 0, then we could now get back two relaxations, one for the right half and one for the left half. And the resulting relaxations could actually be tighter in around the regions that they represent. So if you put those two relaxations together, these represent a tighter upper bound than if you just had this one. right? Okay, so as you're seeing this, the connection that you should be making back to what we're about to do is the ILP is like the blue surface that we're trying to optimize over. It's non-convex. And the LP is going to give us a relaxation of that original objective that's going to be some linear objective. Okay, so now if you continue branching, so now suppose you branch on x2 less than or greater than or equal to less than or equal to or greater than or equal to 0, you could further subdivide and get tighter relaxation still. And if you look at the maximum of all of the relaxed solutions for each of those partitions, that's going to tell you a global upper bound on the entire original function. Right? Okay, and there's this other trick, which is that sometimes you can project a relaxed solution onto the feasible region. So suppose here it was really easy to solve each of these relaxations because they were, say, linear programs. Okay, so that could give you back 4 different blue points. But maybe none of those blue points is actually sitting on the blue surface. So if you had an algorithm that could project it down onto the blue surface, then you could get back a feasible point. Similarly, if the blue surface represented some integer linear program, maybe you could project a fractional solution, a fractional blue point, to an integer red point. Okay. So we say that the incumbent is the best solution that you've found so far. So an incumbent is a feasible solution that you've found. And we can say further that the incumbent is epsilon optimal if the relative difference between that global upper bound, which is the max of the blue points, and the incumbent score is less than epsilon. Okay, so why is that? Well, in general, when we're working with a branch and bound algorithm, what we're really doing is over time we're actually thinking about sort of the value of the objective function and time here. So what we were just talking about was that you have this global upper bound on the objective function, and so the original very loose relaxation is going to give you some value of the objective. But then, once you branch, you might actually get some slightly improved global upper bound if you have, say, 2 of those relaxations. But then you partition it down into, say, 4 regions, and you get another tighter upper bound. And so as you go along, gradually partitioning into smaller and smaller regions, you're going to end up with improved global upper bounds. At the same time, while the algorithm is running, you're gradually finding better and better incumbents. So the incumbent is going to be sort of the best thing that you've seen for a while, but then it'll jump up because you find a new, better incumbent with higher score. So then you keep that incumbent for a while, but then you find another good one. And then that one is really good, and it sticks with you for quite a long time until you find yet another better one. And eventually, if the incumbent score, which is the best you've seen, so far. If it ends up equal to the global upper bound, then what that means is you've actually solved this non-convex problem. So what does that, how does that actually work out? Well, this red line, this incumbent score line, is actually also functioning as a lower bound on your objective. So when they meet, when the upper bound and the lower bound meet, that means that you found a solution, and it can't possibly be better than the current value of the green line. And it's a lower bound because you actually have a real solution. So you know that you can at least get a solution that is this good. So, oh, I had scribbled some notes here. Just slow today. So there's a sort of, oh yeah, question.
I didn't understand how incumbent is given the lower bound. Isn't it the actual solution?
It's an actual solution, or it's the best of the solutions you've found so far. And so a lower bound says, let's go back to a lower bound is saying, you know, for the either mixed or integer linear program, what's a value of C transpose X that is lower than the optimum? That's what a lower bound would tell you. It would say, you know, maybe the true optimum, so let's say you don't know it, but the true optimum is 7. C transpose X is going to be 7. And right now you have something with an incumbent score where its objective function value is 5. So at that moment, you know that there is a solution out there that has objective function value at least 5. So the optimum must be 5 or more. At the same time, if you were able to use that upper bounding to get this green line, and they met, then now you know that say and you find a value of 7 now, an incumbent value of 7. And if you've upper bounded it to 7, then you know that, well, the optimum must be 7 or greater, but you've just upper bounded it, so the optimum must also be less than or equal to 7, which means that you found an optimum.
So just to clarify, the green is corresponds to the red surface, and the red there corresponds to the blue surface.
That's right. So, okay, so basically the branch and bound algorithm is this method for recursively subdividing the search space. And the subspace order can sort of be determined heuristically. So there's lots of different ways that you could actually decide how to recursively subdivide. And then you can actually prune subspaces that can't possibly yield better solutions. So if the subspace upper bound is worse than the current incumbent, then you can actually prune that entire subspace. Okay, so if this upper bound says the best that you can possibly do in this region is a score of 5, but you already have an incumbent that says my objective score is 7, well then you don't even need to look in this whole subspace. You can just prune the entire thing away because you know that you can't possibly do better in that subspace than this red pole. Okay, so there's sort of all of these different ingredients to it. You know, what is the relaxation? How do you do this projection? What are the different search heuristics? And so for integer linear programming, we're going to solve the relaxation using the Simplex algorithm. And then to project a relaxed solution onto the feasible region, one possible solution is actually to do randomized rounding of your variables. So you can actually take variables that have fractional values and randomly round them to integers and see if you get back feasible regions. And this is actually a very common solution. Okay, so where we're going from here is we'll look at sort of a small example of branch and bound, and then we'll move to defining how we can actually set up the map inference problem as an integer linear program. And we'll do all of that probably in the, we'll basically just write this down. And we'll say, look, an integer linear program. And once we've done that, we're basically done with this entire section. So this is sort of the wild part about mixed integer linear programming is there exist these black box solvers that are incredibly powerful and incredibly expensive. So you all probably have licenses to them through CMU. And basically, as long as we can write down the map inference problem as an integer linear program or a mixed integer linear program, then you can just send that off to one of these black box solvers, and it will surprisingly efficiently, in most cases, give you back a most probable assignment. From there, what we'll sort of lead into on Wednesday is a discussion of how you could then use just map inference within learning to actually solve real problems like image segmentation or dependency parsing or OCR. And all of these will be looking at these different ways of actually training, like particularly structured SVM or M3N, where the actual sort of only inference algorithm that you need is one for map inference, and you won't actually need to, say, compute marginals and follow the gradient of the likelihood. We'll actually do, say, max margin learning, where we can do it without actually, say, computing something like marginal probabilities. So that's what we'll get to picking up next time. Okay, see you guys then.